In this video, we're going to go through one linear programming problem that might be a little bit tougher than the ones you've done in the past. One of the main differences about this problem is that it'll have an unbounded feasible region. Remember, the feasible region is always just like the double shaded region or like the main shaded portion of the graph. And unbounded just means that it's not going to be like a polygon that's completely enclosed. It's just going to like open up forever. So let's read through this setup and we'll see some of the other differences about this problem. So Professor Hamer is on a low cholesterol diet. During lunch at the college cafeteria, he always chooses between two meals, pasta or tofu. The table lists the amount of protein, carbohydrates, and vitamin C each meal provides, along with the amount of cholesterol he is trying to minimize. Mr. Hamer needs at least 200 grams of protein, 960 grams of carbs, and 40 grams of vitamin C for lunch each month. Over this time period, how many days should he have the pasta meal and how many days the tofu meal so that he gets the adequate amount of protein, carbs, and vitamins, and at the same time minimizes his cholesterol intake? All right, let's start making sense of this. So we're choosing between pasta or tofu. I see that in the table over here, and then we're given all this information about those meals. And it also says that the table has the amount of cholesterol he is trying to minimize. So that's different than what we've seen before. Usually we're trying to maximize something about the objective function. Here we're trying to minimize the objective function. So the table also tells us this bit about the cholesterol here, and that's going to help us later when we're trying to minimize that amount. So I'm actually going to label that as the objective function, and we'll come back to that later when we're writing the objective function, but that's what that's about. And then back to the problem, it says Mr. Hamer needs at least 200 grams of protein, 960 grams of carbs, and 40 grams of vitamin C. And this is over the whole month. So if you're looking at those numbers and you're just like, whoa, that's way too much, it's for the whole month. And we're talking about getting lunches at the college cafeteria, so you can imagine he's probably working Monday through Friday for weeks a month. So we're looking at buying roughly about 20 meals for the month, and we want to minimize our cholesterol, but we want to make sure that we meet all of these requirements. And that's the other big difference about this problem is we have 3 requirements or 3 constraints that we have to meet instead of the usual 2. So now that we kind of have a handle on the setup of the problem, let's start by defining our variables and writing our constraint inequalities. So I'm going to start by saying that x is the number of pasta meals and y is the number of tofu meals, and that's because at the end of the problem, the real question here says over this time period, how many days should he have the pasta meal and how many days should he have the tofu meal? So we're looking for the number of each of these. And now that I know what my variables are, I can start writing constraints or inequalities about them. Okay, so let's look at what we know about the pasta and the tofu meals. Let's write a constraint inequality that just deals with protein first. Well, I know that the pasta meal has 8 grams of protein and tofu has 16 grams of protein. So 8 times x, because x is pasta, right? So 8 times x, and then 16 times, well, tofu is y, so plus 16y. And this is about protein, so we've got to look back to see how much protein he needs. It says he needs at least 200 grams of protein. So at least, that means that he can have 200 grams. He could have more than 200 grams, that would be okay, but he can't have less than. So we're going to say that if we add all of this protein up from the meals, that has to be greater than or equal to 200. And this is why we're going to have an unbounded feasible region, because we're actually going to be shading like the upper portion of the line. All right, so we have protein. Let's take a look at carbs. So for carbs, we have 60 grams times pasta, which was x. So I'll say 60x plus, and then 40 times tofu, so plus 40y. And looking back into the problem, it said 200 grams of protein, 960 grams of carbs. So he needs at least 960 grams. So again, he can have more than that, he can have equal to, but not less than 960. And then we'll write one more. So for this one's for vitamin C. And actually it's just 2 and 2, so it's the same for each. So for vitamin C, I'll say 2x plus 2y. And again, looking back into the problem, it says 40 grams of vitamin C. That's how much he needs, at least that much, so greater than or equal to 40. All right, so I know what my variables are. I know what I'm trying to find. I know what my constraint inequalities are. That tells me how I'm being restricted in this problem. And let's go ahead and write that objective function right away. So remember, we're trying to minimize the cholesterol. So I'm just going to write myself a little note here that says minimize, just to remind myself later on that that's what we're trying to look for, is actually the smallest point. All right, so the objective function has to do with cholesterol, and we know that there's 60 milligrams for the pasta meal. And we said pasta is x, so I'm going to say 60x plus, and then 50 milligrams for tofu, so plus 50y. And I don't know what this actually equals as like a value, but that's going to tell me the amount of cholesterol that he would consume in a month. So in order to use this objective function, I need to know what I want to plug in for x and y, And remember, those values come from our critical points. So I guess that's my next goal, is we need to find those critical points, and that comes from graphing these inequalities. So let's graph those. So the first thing I'll do is label my axes, since we said x is number of pasta meals and y is number of tofu meals, and then write out my constraint inequalities again, just so we can graph them here. So remember, these are all in standard form, and graphing lines in standard form isn't too hard, but what we have to do is plug in 0 for x and y individually, because what we're doing is we're going to plot some y-intercepts and plot some x-intercepts, and then just connect the 2 points, right? So if it's an x-intercept, that means I don't know what the x value is, but I know the y value is 0, right? So we plug in 0 for y, etc. So I'll start with protein here. I'm going to plug in 0 for x, right? So if I plugged in 0, this x term would just kind of cancel out, and then I'd have 16y equals 200, basically. So to solve for y, I would divide both sides by 16, and you get 12.5. So the y-intercept, the y value is 12.5, that would go right here. And then if I plugged in 0 for y, this would kind of just go away, and then we'd have 8x equals 200, and if we divided both sides by 8, x would equal 25. So that's our x-intercept. And now we just have to connect those 2 points. Now, graphing that line would be like 8x plus 16y equals 200, but this is greater than or equal to 200. We have to shade this. So the way we teach you formally on like how to figure out what side to shade is you'd plug in some test point. And in this case, if I wanted to pick the point like 0, 0, that's not on the line. So that's a great test point to pick, and it's really easy to plug in. If I plug in 0 for x, this just goes away. If I plug in 0 for y, this just goes away, right? So we just get 0 on the left side. Is 0 greater than or equal to 200? No, of course not, right? So we're not going to shade the side with 0, 0, right? That test point was false. It didn't work. So I'm going to shade the other side. Personally, I think the more intuitive way of thinking about it, though, is just thinking about how here we have x and y values being added together, and those have to equal something greater than 200. And that is being represented by this line. So if it's greater than, you have to shade above the line. Like you want to shade all the coordinate pairs x, y that are above the line. So everything up here. Now, any point in this shaded area would fit or would be true in this inequality. That means that any point in this shaded area would get him enough protein, right? So if he bought, like, let's say this point here would be 20 pasta meals and 15 tofu meals, he would definitely be getting enough protein. But we also have to look at carbs and vitamin C. So let's graph this line now. Okay, so we'll do the same thing. If I plug in 0 for x, let's do that first. Plug in 0 for x, this goes away. And now I have to divide both sides by 40 to figure out y. And I believe you get 24 if you do that. So the y-intercept is 24. So we'll put a point way up here. And then if we plugged in 0 for y to get the x-intercept, now we'd have to divide both sides by 60. And if you do that, I believe you get 16. So that's our x-intercept. Again, we just have to connect those 2 points now. And again, figure out what side to shade. Except for, again, we have 60x plus 40y is greater than 960. So you can just kind of intuitively think about this, how it must be everything above this line. So the last thing we have to do here is graph the vitamin C line. So if I plugged in 0 for x, this would just go away, and 2y basically equals 40. If you divide both sides by 2, you'd get y equals 20. So that's our y-intercept. I'll put a point up here on the y-axis at 20. And since this is kind of symmetric here, if I plugged in 0 for y, we'd get the same thing for x, right? We're going to get 20 there as well. So that's our x-intercept. Again, connect the points, and we're going to shade above the line since it says greater than or equal to. All right, so we graphed and shaded all three of these inequalities, and the feasible region where all three colors are shaded is everything up here. So if you kind of see the outline, that would be this down here on the x-axis, following this line up here until they meet at this point, following until they meet at this point, and then following until it hits the y-axis. So we have 4 different critical points that we're going to have to find to plug into our objective function. Now, 2 of them I know for sure. This one is the point 0, 24, and I know that because we found that when we were getting the y-intercept for that line. And then down here, this is 25, 0. Again, we already found that x-intercept for one of the lines, but I'm not sure exactly what these 2 middle critical points are, especially because my graph here isn't perfectly accurate. So we're going to have to use some either substitution or elimination. We're going to have to solve a system of equations to figure out what the coordinates for these points are. All right, so let's do this one first. And according to the color coding scheme here, that would be the carbs and the vitamin C line. So I'm basically going to do elimination with these 2. I'm going to think of them as equations for a minute instead of inequalities. But unfortunately, with what we have right now, we don't have any opposite coefficients. We've got 60 and 2. We've got 40 and 2. Those aren't opposites. So I'm going to take this bottom equation or inequality, I'm going to multiply it by, let's see, I'll do negative 20. 2 times negative 20 will make negative 40, and that'll be the opposite of positive 40. So that would be negative 40x minus 40y, and then 20 times 40 would be 800, so negative 800. Now if I add these two equations together, we've got 60 and negative 40, that would be 20x. 40y and negative 40y cancel, and then 960 minus 800 equals 160. And then divide both sides by 20, so x equals 8. Then I just have to plug that back into one of these. I'm going to use the vitamin C one since that has smaller numbers. So 2 times 8 plus 2 times something, this y value that we're looking for, equals 40. So 2 times 8 is 16. And if I subtract 16 from both sides, we'd have 2y equals, let's see, this would be 24. And then divide both sides by 2. So y equals 12. So that point that we're looking for, that critical point, is 8, 12. And now we have to find this critical point. And according to our color coding, that would be the protein and the vitamin C line. So again, looking at these two equations for a minute, we've got 8x and 2x, those are not opposites, and we have 16y and 2y, again, not opposites. But I'm going to take this bottom line and multiply it by negative 4, and that will give me a negative 8x, which will be the opposite of positive 8. All right, so negative 8x minus 8y, and then negative 4 times 40 would be negative 160. All right, so now I'm really adding the top equation and this new bottom equation. So 8x and negative 8x, those cancel out. We've got 16y minus 8y, that would give me positive 8y, equals, and then on the right side, 200 minus 160 leaves me with 40. All right, divide both sides by 8, and you get y equals 5. And then I'm going to plug that back into one of the two equations that we're using. So either the protein or the vitamin C. Again, vitamin C has smaller numbers. So I'll say 2x plus 2 times the y value we just got was 5 equals 40. All right, 2 times 5 is 10. So when you subtract 10, you get 2x equals 30. And then divide both sides by 2, and you get x equals 15. So we figured out the x and the y value there. We got 15, 5. All right, so we finally found all of our critical points. So the last thing we have to do is plug them all into this objective function and see which one minimizes the amount of cholesterol. So I'll start with the point 0, 24. If I were to plug that into this function, that would be 60 times 0 plus 50 times 24, which is 1,200. If I plugged in the 8, 12, that would be 60 times 8 plus 50 times 12, and that gets you 1080. The next one I'll try is 15, 5, so that would be 60 times 15 plus 50 times 5, which equals 1,150. And the last one, that 25, 0, would be 60 times 25 plus 50 times 0, which is 1,500, actually the biggest one we've gotten so far. So if we want to minimize the cholesterol, that means we want this 1080, that's the smallest amount that we can get, which means we want 8x and 12y. And we said x was number of pasta meals, y was number of tofu. So if he wants to minimize his cholesterol, he should buy 8 pasta meals and 12 tofu meals. And if you add up the 8 plus 12, that would be 20 meals, and that's exactly what we thought in the beginning of the problem, right? About like 4 weeks times 5 meals a week would be 20 meals. So we were able to minimize our cholesterol, and by picking one of these critical points, this 8, 12, we know that's a solution for all 3 of these constraint inequalities, so we know that he's meeting his protein, carbs, and vitamin C requirements while minimizing the cholesterol. So it took a little bit of work to figure that all out, but that's it for our linear programming problem.